Hello and welcome. Today, we're exploring a concept that's shifting from science fiction to real-world engineering, Lunar Resource Utilization, or LRU. Essentially, it's about using resources found on the moon to support space exploration and, potentially, permanent settlements. Think of it as living off the land but on the moon. Why is this so important? It boils down to economics and sustainability. Launching everything we need from Earth is incredibly expensive. Every kilogram sent to the moon costs a fortune in fuel and resources. By using what's already there, we drastically cut down on launch mass and cost. This opens the door for longer missions, building infrastructure like habitats and landing pads directly on the moon using local materials, and perhaps even sparking new lunar industries. So what resources are we talking about? First, and perhaps most crucial, is water ice. Scientists have confirmed its presence, especially in permanently shadowed craters near the poles where it's extremely cold. This water isn't just for drinking. It can be split into hydrogen and oxygen through electrolysis. This provides breathable air for astronauts and, critically, the components for rocket propellant. Imagine refueling rockets on the moon for trips further into the solar system. Extracting this ice involves accessing these dark, cold regions and either heating the ground to capture water vapor or digging up the icy soil for processing. Next up is the lunar soil itself, called regolith. This layer of dust and broken rock covers the moon. It's rich in oxides, meaning it contains a lot of oxygen, about 45% by weight. Engineers are developing ways, like molten oxide electrolysis, to extract this oxygen, again primarily for propellant and life support. Regolith can also be melted or sintered, using solar energy or lasers to 3D print structures like landing pads, roads, or even habitat components. Its bulk also makes it a good material for radiation shielding. However, lunar dust is notoriously fine and abrasive, posing significant challenges for equipment. Beyond water and oxygen, the regolith also contains metals like iron, aluminum, and titanium locked within its minerals. Extracting these requires significant energy for processing, but could yield materials for construction and manufacturing right on the moon. Lastly, there's helium-3, a rare isotope deposited by the solar wind and trapped in the regolith. While theoretically valuable as fuel for future fusion reactors, it's present in tiny concentrations and would require massive strip mining operations to extract a very long-term prospect. Naturally, harnessing these resources presents major engineering hurdles. We need better ways to prospect and map resource deposits accurately. Hardware must withstand the moon's extreme temperatures, vacuum, abrasive dust, and radiation. Power is a huge factor. Resource extraction is energy-intensive, likely requiring advanced solar arrays or even small nuclear reactors. And given the cost and risk of sending people, much of this work will need to rely heavily on sophisticated robotics and autonomous systems. Processing plants need to be efficient, reliable, and require minimal maintenance. Despite these challenges, the path forward is becoming clearer. Programs like NASA's Artemis and the Commercial Lunar Payload Services Initiative, along with efforts from international partners and private companies, are actively testing the needed technologies. Early missions are focused on prospecting for water ice and demonstrating small-scale extraction techniques. Successfully utilizing lunar resources is key to creating a sustainable human presence on the moon and serves as a vital stepping stone for our journey deeper into the solar system. Thanks for tuning in.